In this video, we'll cover regression analysis, specifically an ordinary linear regression using a single independent variable. For our example, we'll use question number 11 from chapter 11 in your textbook, which states, crime-related television shows and movies often paint a picture in which police must go above the law to catch criminals, implying that to do their jobs, the police must circumvent the court's strict rules protecting offenders' civil liberties. Do people who watch these programs come to view the government as being too protective of criminals' rights? To find out, a researcher selected a random sample of people and asked them how many hours of crime-related television they watch per week, which is X, or our independent variable, and the extent to which they agree with the statement that the government is too protective of criminal rights, which is Y, or our dependent variable. And here's our data for 9 individuals. The first thing I'll do is to create a scatter plot showing this data. So I'll highlight the data and then select Insert, choose the Scatter option, and choose a simple scatter plot. And here's our data. Now, first I'll change a couple of the options. So I'll click on the chart elements, and I'll remove the chart title, since that's not very informative, and I'll add axis titles. The y-axis is the extent of agreement with the statement that the government is too protective of criminal rights. So I'll label the axis as government too protective. The x-axis is the number of hours of crime-related television the individuals watch per week. So I'll label that axis crime TV watched. Next, I'm going to change the scale on the axes. So I'll right-click on the y-axis and select Format Axis. And since the responses to this question range from 1 to 9, I'll change the bounds to a minimum of 1 and a maximum of 9. Similarly, since the highest x value is 12, I will change the maximum bound to 12. And that looks pretty good. As you can see, there appears to be a positive association. That is, individuals who watch more crime TV tend to think that the government is too protective of criminals' rights. The last thing I'll do is again select the plus sign and add a trend line. And I'll click on the arrow and select more options. Essentially, a trend line calculates a regression, and we can choose a number of different shapes for our line. We'll stick with linear, and I'm going to select display equation on chart and display R squared value on chart, and then close this menu. This is our regression equation, and R squared is our coefficient of determination. I'm going to go over how to calculate these two values by hand so you know where they came from. The regression line takes the form y equals a plus b times x, where a is the y-intercept, or the value of y when x is 0, and b is the regression coefficient, or the slope of the line, which tells us how much y changes for each unit increase or decrease in x. We'll start by calculating b. The formula for b is simply the sum of the product of deviations divided by the sum of squared x deviations. These terms should be familiar from the video on correlation. I've already calculated the means for x and y using Excel's average function, and so the next step is to calculate the deviation scores, and then I'll square the deviation scores for x. So for the x deviation, it's equal to our x value minus the mean of x. And I'll place dollar signs before the b and the 16 to tell Excel to not move from the cell containing the mean. I can then copy this cell into the remaining cells. I will then do a similar thing for the y deviations, which is equal to y minus the mean of y. To check and ensure that I've calculated these deviations correctly, I'm going to sum the columns using Excel's sum function. And we can see that the deviations sum to 0 for both x and y. Next, I'll multiply the two deviations to get our sum of products. This is equal to our x deviation times our y deviation. And I would like the sum of those as well. Finally, I'll calculate the sum of squared deviations for x, which is simply the x deviation squared. And the sum of those deviations is equal to 158.9. So now I can calculate my b. b is equal to the sum of the products divided by the sum of squared x deviations, or 0.59. A, the y-intercept, is equal to the mean of y minus b times the mean of x, or equal to 4.33 minus our calculated b value times 5.1, or 1.3. As you can see, these two values are equal to the values on the trend line that we added to our scatter plot. We can use this equation as a prediction equation. So for example, for any value of x, or number of hours of crime-related television watched per week, we can predict the extent to which an individual will agree that the government is too protective of criminals' rights. So, for someone who watches 7.5 hours per week of crime-related television, we would predict equal to A plus B times 7.5 that they would answer the statement about the government being too protective of criminals' rights with a 5.75. In addition, we can utilize the correlation to determine a PRE measure, or proportionate reduction in error, that will tell us how much of the variation in belief about the government's stance on criminals' rights can be explained by television viewing habits. First, we have to calculate the correlation. The correlation is equal to the sum of products divided by the square root of the squared x deviations times the squared y deviations. We've already calculated these first two terms in our b calculations, but we also need a sum of squares for y, which I'll calculate now, and is equal to the y deviation squared which sums to 60. So our r is equal to the sum of products divided by the square root, or SQRT, parentheses, the sum of squared x times the sum of squares for y, or 0.96. Our PRE measure, called the coefficient of determination, is simply equal to r squared. In this case, r squared is equal to 0.96 squared, or 0.93. This tells us that 93% of the variance in agreement with the statement is due to television watching habits. The remaining 7% is referred to as the coefficient of non-determination. This is the amount of the variation in our dependent variable that we cannot explain with our independent variable. And we arrive at this by simply taking 1 minus the coefficient of determination. You'll notice that the r squared we calculated again is equal to the coefficient of determination indicated on our scatter plot. The last thing that we can do with regression analysis is to determine its significance. To determine the significance of a regression, we utilize the F statistic, which is the statistic that we've used previously for the analysis of variance. And it turns out that the process is very similar to the analysis of variance. First, we calculate sums of squares, then we use those in conjunction with degrees of freedom to calculate mean squares, and then calculate an F statistic. The sums of squares for a regression analysis are the sums of squares for the regression and the sums of squares of the error. These utilize the sums of squares of the y deviations and our coefficients of determination and non-determination. Our regression sum of squares is equal to our coefficient of determination times our sum of squared y deviations, or 55.8. Our error sum of squares is equal to the coefficient of non-determination times the sum of squared y deviations, or 4.19. Next, we calculate our degrees of freedom. The degrees of freedom for the regression is always equal to 1. The degrees of freedom for the error term is equal to n minus 2. In this case, our n is equal to 9. We have 9 cases for which we have data. And so our degrees of freedom is equal to 9 minus 2, or 7. Just as with the analysis of variance, the next step is to calculate our mean squares, which are simply our sum of squares divided by their respective degrees of freedom. So our regression mean squares is equal to our sum of squares, or 55.8, divided by our degrees of freedom, or 1. Our error mean square is equal to our error sum of squares divided by our degrees of freedom, or 7. Finally, our F ratio is equal to the regression mean squares divided by the error mean squares, or 55.8 divided by 0.6. which gives us an F value of 93.2. We can determine whether this F statistic is statistically significant by using Table D of the textbook, which is the critical values of F. In this case, the degrees of freedom for our numerator is equal to 1, and for our denominator is equal to 7. And so, at the 0.05 level of significance, we have a critical F of 5.59. Since our calculated F is far greater than our critical value, we can say that our regression results are significant. Generally, the results of a significance test for a regression are presented in an analysis of variance summary table similar to this. The total are simply equal to the sum of the regression and error sum of squares and the sum of the degrees of freedom. To summarize, based on our data, we calculated a regression equation of y, which is the extent to which participants agree with a statement that the government is too protective of criminals' rights, is equal to 1.3 plus 0.59 times x, where x is the number of hours of crime-related television watched per week. We also determined that the number of hours of crime television watched accounts for 93% of the variation in statement agreement, and that this relationship was statistically significant.